Hi everyone, I'm Zhe Huang from Human-Centered Autonomy Lab, University of Illinois at Urbana-Champaign. I'll present our work on seamless interaction design with coexistence and cooperation modes for robust human-robot collaboration. This is a video of a collaborative robot solution for BMW Mini crash can assembly. The collaboration part of the assembly task is that the human needs to align 4 pop rivets to machine holes, and the robot needs to install the rivets. Essentially, the human is responsible for the task that requires dexterity, and the robot performs non-ergonomic installation. The human and the robot work in parallel to reduce assembly cycle time. Besides labor division, the robot solution also includes other key features. For example, human safety is enforced by contact detection. If rivets are misaligned, the robot can try repeatedly until success. When the human has not finished the job, but the robot has reached, the human can push the robot away where the switch to compliant mode is by contact detection. After the human has finished the job, the human can press a button to switch the robot back to autonomous mode. The collaborative robot solution shows impressive performance gain, but we can still see a lot of potential for further improvements. For safety enforcement, contact detection receives signals to stop robot after the contact accident between human and robot has already happened. Can we use vision to prevent these accidents from happening ahead of time? Repetitive trials can work for failure recovery because slider rivet misalignment can be effectively detected and can be easily recovered. However, this does not work when failure patterns are complicated and requires human check. And it won't work either when the misalignment is severe, then needs human intervention. The goal-directed motion trajectories are pre-programmed. So when the human does not finish her alignment job within the required time, the predefined following actions from the robot will map things up. The switch from autonomous mode to a compliant mode is through contact detection, but reverse mode switch works by pressing the button. Can we make the mode switch natural along both directions? To address these challenges, we argue that the key is to perform effective human tracking and the human behavior modeling in the collaborative robot system. Here, we formulate the requirements on human-robot collaboration as a problem that a human-robot team is assigned multiple goals, which all require efforts from both the human and the robot. The human needs to lead the team to accomplish all the goals in a desired task sequence, which is not known by the robot in advance. The robot needs to make full use of observed human behavior to safely and efficiently collaborate with the human. In addition, we create a use case that is similar to the previous assembly task. In the previous task, the human is responsible for aligning 4 rivets, and the robot performs rivet installation. Here, the human is responsible for aligning 4 male parts from a preparation area to the female parts at predefined locations. And the robot's task is to push all male parts into female parts to finish the assembly. We introduced the coexistence and cooperation CoCo system to resolve the problem and demonstrate the system in the use case. The inputs to the system are force torque measurements, robot proprioception, and human body poses, and outputs control on robot joint velocity. The human intention tracking module is inspired by our previous work, mutable intention filter. The human hand position is used as input to track task intention, which in our use case is the desired goal region where the human aligns the part. Both the end effector position and the human hand position are used as input to track whether the human wants to work without interruption or manually guide the robot, which is the high-level interactive mode intention. We use track the task intention to create the task plan. The robot will follow the task plan in the coexistence mode. During the coexistence mode, the robot and the human work on the jobs separately assigned to them. The robot and the human merely exist in a shared space and do not intend to interrupt each other. The robot needs to avoid the human and to perform non-ergonomic assembly actions. During the cooperation mode, an assembly failure needs to be recovered by the human realigning parts and the robot performing the pushing action again. Because the human identified a failure, the robot needs to be manually guided by the human to where the failure happened. When the tracked interactive mode intention indicates human wants to work on his or her own tasks, the coexistence mode is switched on to provide control command. When the tracked interactive mode intention indicates human wants to guide robot to perform failure recovery operation, the cooperation mode is switched on to provide control command. Next, we will demonstrate our implementation. We implemented open pose on multiple camera views. We also performed common filtering and tracking heuristic to provide reliable tracking on human wrist even under occlusion from robot. Here, we demonstrate task intention tracking. Task intentions are predefined task-related goal locations, where the human will reach during the task. Human wrist position is used as input to track task intention. During the coexistence mode, the robot receives goal position signal based on tracked task intention. Robot will reach the goal while avoiding human by artificial potential field. The force measurement is used to detect the pushing action is accomplished. Finally, here is the demonstration of the overall CoCo system in the use case. We can see that both interactive mode and task intention tracking can provide reliable tracking. And the robot followed the order of humans' part alignment to push pairs of parts together. When an assembly action failed due to an inappropriate pushing point, the human noticed the failure, realigned part, and then reached to the robot in order to guide the robot for failure recovery. After the desired location is reached, the robot switched from cooperation to coexistence mode and recovered the failure. This work was done by our team led by Professor Catherine Driggs Campbell and was supported in part by ZJU UIUC Joint Research Center project through the Center for Adaptive Resilient Cyber-Physical Manufacturing Networks, funded by Zhejiang University. Here are some takeaways of this work. Collaborative robot solutions are entering the industrial market, and current practice has huge potential for improvement due to lack of effective human tracking and human behavior modeling. Seamless and robust human-robot collaboration can be achieved by integrating coexistence and cooperation interaction modes with human intention tracking. Human intention tracking takes human wrist positions as input to track low-level task intention, and uses the task intention along with human risk positions and robot artifacting positions to track high-level interactive mode intention. We demonstrate our system on a use case analogous to a real-world multi-step assembly task. Thank you.